Greetings. My name is Dr. Sibukhudi. I'm currently lecturer at the University of Johannesburg. So we'll be taking this journey together. The sole purpose of this classes is to prepare you as you're busy with while you're waiting for your matric results. Because honestly, there's a huge gap between high school mathematics and university mathematics. So basically these lessons are just to prepare you, and because remember that maths is based on, or maths feeds other subjects, meaning subjects like physics, your chemistry, your other subjects, stats, actual science, they're based on maths. So basically it means that actually if your performance in maths is not so good, it could end up affecting other subjects. So basically that's what we're trying to do. Hopefully you enjoy. And again, we need a lot of engineers, we need a lot of doctors, we need a lot of scientists here in South Africa. I mean, right now you could see that during the pandemic, there had to be some doctors that had to be asked from Cuba to come and help us as if we are incapable. So the whole purpose is that the whole purpose of this lesson is trying to see if we can broaden affiliation into them for people that want to do mathematics, that they want to be scientists at large. So basically what we did, regardless what course you're going to do at university, what science course, whether it's a BSc or what's engineering or whatever, as long as you're going to do maths, this is the general maths that gets to be done, whether you're going to UCT, whether you're going to, because basically what I did, I went around all these universities and actually went to check what kind of syllabus do they do. So basically all these syllabi got to combine them and make these topics. So basically we're going to have these 2 weeks of discussions, discussing these topics, just to give you an introduction. Obviously, there's a lot that needs to get done before you get here. The syllabus is very huge. So obviously we cannot do syllabus in 2 weeks, but basically these topics are just supposed to give you just a bit of highlight of what to expect or what's out there. So I hope you enjoy. I think for now, we can start with our classes right away. Yes. Gonna be switching my camera because I don't think you guys need to see me. But otherwise, our first lesson here, we're going to be discussing a limit of a function. What do we mean when we say a limit of a function? So obviously, there's going to be notations that you guys maybe are not familiar with so far. So we'll get into that later on and get to explain where does the notation come from and what does notation mean. So I'm going to switch my camera off for now so that we can concentrate on the topic. Okay, let's start first. So basically, we said we're going to be discussing a limit of a function. Let me see if I can write here. So we're going to be discussing a limit of a function. So basically, from this limit, what do we mean a limit of a function? So basically, a limit of a function, we're talking about how we just get to investigate how a function behaves near a certain value in the domain. Remember, domain is the values of x where the function is defined. So we get to look actually how does the function behave around some certain x value in the domain. Let's take, for an example, let's take a parabola. I hope you all know what a parabola is. So this function, x squared minus x plus 2. So basically, we want to investigate how does this function get to behave around the value of 2 when x is equal to 2. Because I mean, the parabola is defined everywhere, but now we just want to know we don't care what happens at 2 when x is equal to 2. We just want to know how does the function behave around x is equal to 2. So what we did here, we have our function. Remember that our function is the same thing as y. So we can take this as the y values. So what we did, all the values around x. So obviously these values are the ones that are less than x. I mean, when x is less than 2, right? So we took 1, 1.5, 1.8 and all that, and these are the values that are greater than 2. So you can see 3, 2.5 and all that. So basically we said we want to see around. So that's why we take the values that are smaller than and others that are bigger than. But now we get to see that actually these values, as we increase the x values, when you look at the corresponding y values, remember x is the independent variable, y is the dependent variable. So as we get x to be closer and closer to 2, the values of y, they get to be closer and closer to 4. I hope you can see that even from the right-hand side of 2, all the values that are greater than 2, as we decrease them to get closer to 2, as we decrease the values of x, the corresponding y values, they also get closer and closer to 4. I believe you can see from here, there's a pattern. So meaning if maybe we take another value that is closer to 2 and maybe say take 1.999, we expect this corresponding y value to also maybe this 7 also to maybe to get to 9 as well, and just keep on getting closer and closer to 4. So from here, I believe we can, maybe let me just erase this. I believe from here we can all agree that as x gets closer to 2, the corresponding y value, it gets closer to 4. Basically the function, that's how the function gets to look like. Maybe let me use this pen rather. The pen here. Okay. So basically, we can see that this is the function. And for this function, as the x values are getting closer to 2 here, the corresponding y values are getting closer to 4. Even from here, when you take the values of x that are greater than 2, getting closer to 2, decreasing them to get closer to 2, the corresponding y values are getting closer to 4. So we can see that from this figure, as x gets closer to 2, y or the corresponding y values get closer to 4. So now what we can read from here is that actually if we want y to be closer to 4, all we need to do is just to take x to be closer and closer to 2. So basically, like if we just take values that are sufficiently closer to 2, the corresponding y values will be closer to 4. That's what we can read from our table, or that's what this table is telling us. So basically, from what we've learned, or what we have so far, we can say that the limit of the function, this function f of x, is equals to the parabola x squared minus x plus 2, as x approaches closer to 2, then the limit of this function is 4. I hope that part is clear, because now we get, remember, we're trying to define what the limit is. We say that the limit of a function of f of x, the limit is 4 as x approaches 2. That's how you can read it. And this is how, this is the notation that we're going to use to try to explain the same thing. So basically, we can see that the limit of f of x as x approaches 2 is equals to 4. And this is, so now let's, so basically from what we've learned, this is what we can come up with. So let's try to see if we can generalize this and come with a definition of a limit. So suppose this function, because I mean, the previous example was specific, we had the specific function. We knew it was a parabola, but suppose that we have this function, we don't know whether it's a hyperbola, it's an exponential function, it's a straight line, we don't know. But suppose we have some function, let's call it f of x, and this function is defined some x value, and this value of x is a. So basically, we don't care what happens at a, we just want to see around this a, because remember in the previous example, our a was 2. So now we're trying to generalize, we don't want to be specific. So we say that suppose we have this function f of x that is defined when x is near some number a. So now, again, we don't care what happens at a, we just want to see around a what happens. So we write the limit of f of x as x approaches a is equals to L, and this is how we read it. The limit of f of x as x approaches a is equals to L, right? And that it means that if we make the values of f of x to be closer to L, or we can make the values of f of x to be closer to L. In the previous example, our L was 4. So we can make these values of f of x to be closer to L as we want, as long as we take the values of x to be closer and closer to A. So basically, for us to be able to say that, or for this notation, that's what it means. It means that we can make the values of f of x to be closer to L as much as we want, as long as we take the values of x to be closer to A. We don't care what x is equals to A. We want to talk about the part when x is equals to A. There's a specific term for it. It's called continuity, but we'll get to that point in the next coming lessons. Okay, so from this definition, basically what we're saying, we came up with, we explained this notation. So basically, another way of saying this notation, just say f of x is approaching L, or f of x goes to L as x approaches A. Done. So the notes that we can get from the definition is that we don't care when the A is equals to A. We just want we want the part when x is closer to A, but not equals to A. That one is very, very, very much important. For example, if you look at these three functions, let me see if I can zoom in so that we can wait. So let me just So if you look at these three functions here, the functions that we have here, you can see that figure A, our function is just smooth. It is smooth all the way. So we can see that as x approaches A, remember A is here. So these are from the x-axis. Obviously, the corresponding x values will be somewhere here. So or the corresponding x value will be here. So as we approaches A, you can see that the y values will be approaching L as well. And as from the corresponding x values from here that are bigger than A, that are when we're approaching A, the corresponding y values will be approaching L as well. If you look at figure B, if you look close, you'll see that actually this part we have some open dot. So this open dot, it means that actually, if you substitute f of A will not be L. Meaning, remember that A is a value of x. So meaning if from that function of f of x, if you substitute A, you will not get L. Here you will get L, because you can see that L corresponds to A and the function is just smooth. But here, because we have this open dot, it means that actually if you substitute this f of A, the y value that you'll get from there, it will not be L. But this dot that is here, it means actually this will be the y value that you'll get. And such function, they are said to be piecewise function. In this case, you can say that it's piecewise smooth, meaning all the values in the domain are defined, or they have the corresponding y value. They're just not at the y value that you're expecting, but otherwise the y value will be here. But if you look at figure C, we still have this open dot. So meaning if you substitute A into the function, you will not get L. But looking at figure C, comparing it to B, at B we had this dot, but for this figure C, we don't have any dot anywhere. So that would practically mean that actually at A, the function is undefined. So meaning you cannot substitute A. But otherwise, we can see that when we look at the corresponding x values as we're approaching A, we can see from the left, and the corresponding x values approaching A from the right, all the y values are also approaching L. So we can say that the notation that we used earlier, we can still use it here. I hope you guys can see what I'm talking about. So here, we do not have f of A, it's undefined, but here our f of A is this blue dot here, and in this case our f of A will be L. Okay, let's continue. Sorry, let's continue our class. Okay, let's okay. So now let's continue. Let's take for an example. We have this function, and this function, you see, we are asked to find the limit as x approaches 1 of x minus 1 over x squared minus 1. I believe you can see already that actually at 1, this function, because this will be our f of x, isn't it? So basically, this x minus 1 over x squared minus 1, this is called a rational function. It's when you have a function all over another function, but otherwise, these kind of functions, they are called polynomials. If you have time, please Google that, what is a polynomial, but this kind of function is called a rational function. So obviously, you cannot substitute 1 because here, 1 squared is 1, so 1 minus 1 is 1, and we cannot have 0 in the denominator. That such function, we say that it's undefined. But otherwise, like we said, we don't care when x is equals to 1, we just care what happens when x is approaching 1. I think whatever that is said here is what I just explained. So let's try to see if you can use the table again. We took the values that are less than 1 and the values that are greater than 1, and all of them actually they are approaching 1. So we want to see the independent variable. We took 1.5, 1.1, just like that, and you can see that the corresponding y values or the corresponding f of x values, they are also approaching 0.5. I hope you believe you can also see from your side. You can see from 0.5, 0.9 increasing to approach 1. The y values are decreasing to approach 0.5 coming from the left. So it is fair, or we can guess that actually the limit of x minus 1 all over x squared minus 1, as x is approaching 1, we can say that it's 0.5. And basically, this is how the function gets to look like. We can see that here, as the x value is approaching 1 from the left, and from the right, the corresponding y value respectively approaches 0.5 from above and from below. And you can see here we have an open dot, and this open dot, it actually means that actually at 1, the function is not defined. So meaning you cannot substitute 1 into the function, you'll get undefined. Actually, here we can define another function, because from this f of x, we can see that at 1, the function is not defined. We can have this another function, we can call it g of x, and we say that actually when x is 1, let's say the corresponding y value at that 1, it's 2. Please note that we don't get this 2 from this function here, from the x minus 1 all over x squared plus 1. We just said we could say that this at x is equals to 1, the value is 3 or it's 5. We just give it a value, but it does not come from x minus 1 all over x squared minus 1. We just give it a value because at 1, the x minus 1 all over x squared minus 1 does not have the corresponding value when x is equals to 1. So we say when x is 1, let's just give it a y value and just say it's 2. So such function, it will have the same limit. Remember, we said the limit, we don't care where at that value, we just want to see what happens when you approach that value. So basically, even for this g of x, as x approaches 1 from the left and from the right, the corresponding y values approach 0.5 from above and from below, respectively. So even though our corresponding y value is at 2, but our limit, it is still 0.5. I hope that was clear. Let's take another example here. And I hope I'm not fast. So basically, for this example now, we want to estimate the value of, or the value of this limit. So basically, we want to see what happens when t approaches 0 for this function here, t squared plus 9, the root of t squared plus 9 minus 3 all over t squared. So we want to estimate. So obviously, we can see from here that at 0, the value is not defined because you'll have 0 in the denominator. So for that, we want to see what happens when the values of t are approaching 0. We don't care what happens at 0. We want to see what happens when it approaches 0. So if you use the table again, obviously here I would just put the plus minus because I mean we have t squared here. So the corresponding, the y values will still be the same for t being positive and for being negative. So we get the same y values. But from here, we can see that actually approaching 0, taking the values of t taken from 1, 0.5, 0.1, approaching 0 like that, coming from the left and coming from the right. The corresponding y values, we can see that they're approaching 0.16, and actually the closer we get to 0.1, the values approach to be 0.1666666 like that. And remember that 0.166 recurring like that, that is just 1/6. So basically means we can guess that as t approaches 0, the values of the function, they approach 0.116, 0.16 recurring. And that is 0.16 recurring, that is 1/6. So we can say that the limit as t approaches 0 of the root of t squared plus 9 minus 3 all over t squared, it's 1/6. So now, this brings us to another discussion, our one-sided limit. So basically, we've been talking about limits here, and I believe we understand what limits are. But now we want to define what do we mean by one-sided limits. So let's take for an example, this function is called a Heaviside function. So this function, basically, you can see that for the values of t is a function of t. For t values being negative, we get 0. For the values of t being positive, we get 1. So basically, this function, if you were to draw it, and maybe let's say these are the values of t and the y values, or you can say h, if you like. We say when t is negative, let me see if I can use a different color. Let me see if I can use a different color here. Okay, I can see where can I use the color. Just give me a minute. Okay, I can see where to use the color. So otherwise, when t is negative, remember t is negative on the side because this is our origin. So it means that this function, we can say that actually it goes on top of the t-axis here when t is negative, and when t is positive and including, remember this inequality means including, so it's 1. So if 1 is somewhere here, so it means actually we are going to have a shaded dot here and just going all the way that direction. So this function, basically this is how it goes, it gets to look like. So basically now we want to evaluate limits, but only looking at one side. So from that function, we can see that actually, remember that we want to see, we evaluate the function when t approaches 0. So basically, if you look at the function that we do here, if we are approaching 0 from the left, we can see that actually we are, the corresponding y value will be 0. And coming from the right, meaning coming from the positive side, the corresponding y value, it approaches 1. So for that, when that is the case, you can see that these y values, they are not the same. So if they're not the same, we say that the limit does not exist because the values of h of 3 are approaching 1 coming from the right, and the approaches 0, h of t is approaching 0 coming from the left. So when the limits are not approaching the same, or when the y values are not approaching the same value from the left or from the right, as we say that the limit does not exist. And that's what we mean when we talk about the one-sided limit. So now, when you talk about coming from the left, remember here we're talking about coming from the left, meaning coming from the negative side, if you like. This is the notation that we use. So meaning looking at this function, t approaching 0 from the left, the corresponding y value approaches 0. And coming from the right, t approaches 0 coming from the right or coming from the positive side, the corresponding y values are approaching 1. So basically, this is the notation that we use. So here, this little negative here, this exponent that is a negative here, this just means that coming from the left, and this positive here, it means coming from the right. I hope that part it's clear. So this notation, like I said, t approaches 0, this just indicates the values that have t that are less than 0. Remember that we're approaching 0. So this minus, it just means that the values that we're using are approaching 0. It does not necessarily mean that they're negative. Well, in this example, they are negative, but this smaller, this exponent that is a negative, it does not mean that the values that we are using, they are negative. It just means that the values that we are using, they are smaller than 0. And this exponent that is a positive, it does not mean that we are using the positive values. It just means that we are, when using the values that are bigger than 0, I mean, I'm talking 0.5, 0.2, 0.1, 0.01, just like that. So we're approaching 0, but coming from the right, meaning using the values that are bigger than 0. That's what this notation means. And to put it, to generalize it and put into a definition, so we're saying that the left-hand limit, so that's what we call it. That, remember that from here we see that we have this negative here that is an exponent. So we call it the left-hand limit of f of x as x approaches a, or the limit of f of x as x approaches a from the left is L. That's how you just read it. Meaning we can make the values of f of x to be closer to L as much we want, as long as we take the values of x to be closer to A as we like from the left. So that's how you read it. And we call this the left hand, we call such a left-hand limit. So obviously, I believe from that you can expect that there's such thing as the right-hand limit, and actually is defined the same way. The very same we've been defining the left-hand limit, the right-hand limit gets to be explained the same way. So this, again, the symbol x approaches a to this power exponent plus, it does not mean that we are using the positive values. It just means that we're using the values that are great of x, that are the values of x that are greater than a. And maybe we can use these two functions to explain what we just meant. So we said x is approaching a. We just look from the left, and for this figure here, x is approaching a, coming from the left, from the right. So meaning we are using the values that are bigger than x. Remember from our Cartesian plane going to the far right, the values of x are increasing on the x-axis, and here. So meaning these values are less than a, and the values here approaching a from the right, we are using the values that are greater than a. I hope you can see that even from this figure here, x is approaching a, and we are on the side that is on the x-axis when the x is positive. But we are using the values of x that are smaller than a. So that notation, it does not mean that we're using the negative values. So now, if you compare those two left-hand limit and the right-hand limit, they bring us to this definition. Remember earlier on we defined what we meant when we said a limit, and there was that example when I said we say that the limit does not exist. So the limit, we say that the limit exists if the left-hand limit and the right-hand limit are the same. So if the left-hand limit and the right-hand limit are the same, we say that the limit exists. Or that's when we can say that the limit of f of x is L as x is approaching a. So this is the only time we can, this notation is true, or this is only true. That's why we have if and only if. If and only if it means strictly. Strictly, so we can say that the limit of f of x is L as x approaches a, if and only if the left-hand limit and the right-hand limit are the same. Maybe let's take an example to explain what we just meant. We have this function here. So we don't know the formula for this function. We don't know whether it's a parabola, it's a hyperbola, it's a mix of the two. We don't know. It's a rational function. We don't know this function and we don't care. But otherwise, we've just been given the geometric representation. The graphic representation of the function, and these are the questions that we are asked. So basically, number A is asking us, what is the limit of g of x as x is approaching 2 from the left? And you can see that, for example, number E is asking the limit of g of x as x is approaching 5 from the right. So I hope that part that this means negative, it does not. It just means using the values that are less than 2, and here it means that actually this plus here, it means using the values that are greater than 2. It does not mean negative, does not mean positive. We're just saying that we are using the values that are less than that number that we're approaching. Let's look at number A. Number A, so here's our g of x. X is approaching 2. X is 2, it's here. So coming from the left, it means actually we have to use the values of x that are less than 2. So it means actually on the left side of 2, it means we're going to use this function here. So it means actually approaching 2 coming from the left, the corresponding y values, we could say that actually they are approaching 3. So we can say that the coming from the left, g of x is approaching 3. I hope that part is clear. We are using this because we're saying that we're approaching 2 from the left. But if you look at number B says that we're approaching 2 from the right. If you're approaching 2 from the right, it means we look at the values of x that are greater than 2. So we're talking about your 5, 4, 3, 2. Sorry, not at 2, 3, 2.5, 2.2, just like that. So it means we have to use this part of the function. So we can, I believe it's fair to say that actually approaching 2 from the right, the limit or the function is approaching 1. Or we can say that actually this will be equals to 1. I hope that is clear. And if you look at number C, we're just saying that x is approaching 2. So basically this, it goes without saying, it's basically comparing the left-hand limit and the right-hand limit. So here, because we're coming from the left, we get 3, coming from the right, we get 1. We say that the limit does not exist. So I'm just going to write D and E just to say it does not exist because the limits are not the same. And please, very, very, very much important, please note that at 2, if we substitute 2 into this function, you can see here we have an open dot here and we have another open dot here. It means that the function is not defined at 2. But again, like I said, for the studies of limits, we don't care what happens at 2. We care what happens around 2. And I hope that part is clear. Number D, we're talking about approaching 5 from the left. From the left, obviously, we said we're talking about the values of x that are less than 5. So meaning we're using this part of the function. So you can see that actually, I think this is 2. I think so. So we can say that actually the limit is 2 coming from the left. I think that part is clear, or that part, I believe you can see that. And coming from the right, we still use the same function, but looking at coming from the right, we're approaching the same function here. So we say that also the limit of g of x as x approaches 2 from the right also equals to 2. So number F, we can say that actually because coming from the left, approaching 5 from the left and approaching 5 from the right, we get the same value. So we can say that actually the limit of g of x as x approaching 5 is equals to 2. I hope you can see here we said does not exist because you're approaching different values coming from the left and coming from the right. But here, because coming from the left and coming from the right, we approach the same value, that value, it becomes our limit. And please note that here, for this function at 5, if we substitute x is equals to 5 into this function of g, we're going to get this value. I'm not sure if it's a 1 or a 1 point something, but otherwise this blue dot here, it means that is the corresponding y value when x is equals to 5. And that value does not equals to our limit. So hence we say that we don't care what happens at that specific point. We just want to see what happens when you approach that point. And again, for enrichment, or if you want to study ahead, we said that actually we're going to talk about continuity when you want to compare the value at that specific point with the limit approaching that point. So basically, you can go and maybe read on meaning continuous, meaning continuity. I hope the spelling is right. Hey, this English. Yeah, so you can go and Google on continuity or limits versus continuity. You'll see actually the continuity is the one that gets to talk about what happens at specifically at that function, but otherwise at that point. But like I said, we'll discuss that in detail in our next coming lessons. I'm going to skip this because this is what we just explained. So now let's talk about infinite limits, because sometimes these functions, because so far our limits have been approaching certain value, been approaching 2, approaching 4, and all that, approaching L in general. But otherwise, it's not always the case that actually as X is approaching a certain value, the Y will be approaching a certain value as well. Let's take for an example. So I'm going to explain these infinite limits using this example. Let's say we want to find the limit as X approaches 0 of 1 over X squared, and want to see if actually the limit exists. Remember we said the limit exists if coming from the left and coming from the right, it gives us the same limit. So if we go back to the table method, and again, I should emphasize this, we are only using this table method just for understanding. But otherwise, throughout the course, or when calculators are not allowed. So you don't have time to be substituting these values to see what is happening. And in our next lessons, we'll be showing you how do you evaluate this without using the table. Because honestly, in mathematics, or the mathematics that kind of mathematics that you guys will be doing, you don't necessarily need a calculator. Actually, you don't need a calculator. So in our next lessons, we'll be evaluating these limits, but not using a function, not using a calculator, just being able just to evaluate them. So for now, because we're still trying to lay foundation, we want you to understand what we mean when you talk about limit. That's why we use these table methods. So because we have X squared here, obviously the X values being positive and being negative will be the same. So we can see from here actually that when we approach 0, coming from both the left and the right, as we decrease or increase the X values, approaching 0, you can see that the corresponding, remember these are the Y values. So the corresponding Y values are getting bigger and bigger and bigger. So obviously it means if here maybe we take another value of 0.0001, it means actually the corresponding Y value will be bigger than this 1 million. So for that, we say that because we are not approaching a specific value, we say that the limit does not exist. So meaning so far we have said there are 2 ways for you to say the limit does not exist. It's when the limit from the left and the limit from the right are not approaching the specific value, or when the limit it's not approaching a specific value. The limit from the left and the limit from the right are not approaching the same specific value. So that's the first type of, or that's the first way you can say the limit does not exist. The second way is when the corresponding Y value does not approach a certain value. And that's so because the value gets bigger and bigger, we say that the limit goes to infinity. And doesn't mean we just here because we wrote is equals to infinity, it means that infinity is not, it's a number. Infinity, it's not a number. It's not a number. It's just the symbol we use just to say that actually the values are getting bigger and bigger and bigger. Yeah, so basically we use this notation to say that f of x tend to become very larger and larger, or we can say that it increases without bound as x get closer and closer to a. And to put it into a definition, this is how we put it. So to generalize, we say that let f be some function that is defined on both sides of a, except possibly at a. Remember we said for here we're talking about limits. We don't care what happens at a, we care what happens around a. So then the limit of f of x as x approaches a, it goes to infinity. It means that actually the values of f of x can be made to be bigger and bigger as much as we want by just taking the values of x to be closer and closer to a. That's what this definition means. Another notation for this, we can say that f of x goes to infinity as x approaches a. Please remember again, infinity is not a number. It is just a symbol, it's just an expression. So basically, this expression, like I said, it just means f of x is increasing without bound as x is approaching a. So for example, you can look at this figure here. It means coming from the left, coming from the right. That function, remember, it was 1 over x squared. No, but basically we say that if x approaching a, we say that the function goes to infinity. You can see that coming from the right, it goes to positive infinity. Coming from the left, it goes to positive infinity as well. So in that case, you can say that the limit of f of x as x approaches a goes to infinity. And actually, the same definition goes to negative infinity, means the function, the values of y, they are decreasing without bound. So we can, so negative infinity, or what we can define that saying that let f be some function defined on both sides of a, then the limit of f of x as x approaches a goes to negative infinity. It just means that the values of f of x can be made to be arbitrarily large negatively, or you can say that it becomes smaller and smaller and smaller. Remember that negative numbers are smaller numbers. I believe from the x-axis, remember 0, 1, 2, 3, and here you have -1, -2, -3. So in other words, -3 is less than -1. So it means actually this negative infinity means actually the values are just becoming smaller and smaller. They become large in a negative way. And we can make that by just taking the values of x to be closer to a as much as we want. Again, remember that the notation of limit of f of x as x approaches a goes to negative infinity just means that f of x is decreasing without bound. Meaning it does not get to a specific value, it just keeps on decreasing and increasing as x approaches a. So basically you can take, for an example, -1 over x squared. The limit as x approaches 0, the function will go to negative infinity. So for you to say the function goes to positive infinity means coming from the left and coming from the right, both of those functions are going to infinity, just like we said in type 1. And again, for you to go, the function goes to negative infinity, you should mean that actually coming from the left and coming from the right, both of those functions or both of those values should be going to negative infinity. Let's take maybe the geometric, let me just zoom these functions in. This function, if f of x, as x approaches a, you can see that f of x goes to positive infinity. And here, coming from the right, f of x goes, as x approaches a from the right, f of x goes to positive infinity. And here, for number C, figure C, as the limit as x approaches a from the left, the corresponding y values go to negative infinity. And lastly, figure D, here f of x goes to negative infinity as x approaches a from the right. So this is what we mean if maybe you need a graph or a graphical representation for you to be able to see what you're talking about. And so basically, and now, again, before I forgot, these lines, because the function goes to negative infinity, meaning the function does not touch that line because it does not go to a specific value. And these lines, we call them to be vertical asymptote. And please put in the emphasis on vertical because there are other types of asymptotes. So this, the one that we've been talking about so far, we call these ones because x is approaching a specific value. So meaning we have a vertical line at a that the function does not touch. Because otherwise, if the function was touching that line, then we'll be having a corresponding y value. But otherwise, we do not have the corresponding y value. Otherwise, the values of y just keeps on getting either bigger and bigger, meaning if you're going to infinity, or getting smaller and smaller, meaning going to negative infinity. So such, we call them to be vertical lines. There are horizontal lines, horizontal asymptotes. There are diagonal asymptotes, just like that. And you'll get to see those in the next coming lessons, especially when you get to draw a graph. Maybe let's see if we can get an example. So now we are asked to evaluate this function. We have this function 2x over x minus 3. Remember I said this type of function, this is called a rational function. Please go and Google what is a rational function. The rational function, just to give you a clue, is when you have a polynomial on the numerator and another polynomial on the denominator. I know that polynomial, it's another term. You can go and check on that term, what is a polynomial. If maybe you want spelling, polynomial. That's just how you write it. So you can go and check on the term, what does polynomial mean? So as I said, this is a rational function, is when you have a polynomial over a polynomial. So now from this example, we have this given this function 2x over x minus 3, and we're asked to evaluate the limit coming from the left as x is approaching 3 from the left and from the right. So now let's look at this value, right? We don't want to use a calculator. I'm just giving a hint for the next lesson. So if coming from the right, it means that we are using values. Remember, 3 is a positive number. So if you're approaching 3 from the right, it means that actually we are using the values that are bigger than 3. I'm talking about your 4, 4.5, for a 4, 3.5, 3.2, 3.1, just like that, approaching 3. So those values, because they are bigger than 3, it means on the denominator, 3.5 minus 3 is 0.5. So it means actually on the denominator, we'll be left with a positive value. And obviously here we have 2x, so 2 times 3 or 2 times a positive number is still a positive. So it means actually the value that you'll get here, obviously we cannot substitute 3 because 3 minus 3 is 0. So for that, it means actually approaching 3, because at 3 is not defined, it means actually this function will not go to a specific value. The values will just keep on increasing and increasing and increasing. It means actually we'll be going to positive infinity. I hope you can see that. For example, let's see here, we took the value of x to be 3.01, getting closer to 3. If you substitute that value, we see that on the numerator, 2 times 3.01 becomes 6.02, and then on the denominator, 3.01 minus 3, it becomes 0.01. So obviously dividing the 2, you get 602. You can see that actually the closer we get, the bigger the y values get. So you can take another value, say maybe 3.001, substitute it and see actually what happens. But otherwise, we get to see that here, the corresponding y values will be approaching infinity. So we say that the limit coming from the right, so x approaching 3 from the right, the function will be approaching positive infinity. And the same thing happens when you approaching 3 from the left. And the numerical value just becomes large, very large negative number. That makes sense. Look at the function here. The values, remember, coming from the left, it means that we're using the values that are less than 3. Those values will still be positive. Let's say 2.9, 2.95, just like that. 2 times a positive number will be a positive number. The denominator, a number that is smaller than 3, let's say 2.5. 2.5 minus 3, to be a negative. So basically means that actually we expect our limit here to go to negative infinity. So so this is how the function gets to look like. You can see that from the left, we are going to, coming from the left, we approach, the function goes to negative infinity, and coming from the right, the function goes to positive infinity. So basically in this case, if you are asked what is the limit, as meaning the limit, let me see if I can write, approaching 3 of this 2x all over x minus 3. So because coming from the left and coming from the right are not the same, we say that the limit does not exist. And we'll stop here for today. Thanks a lot attending. I'll see you on the next lesson. Toodles.